Beneath its thick veil of clouds, Venus is a world of extremes. Its surface is scorched by temperatures that could liquefy lead, and its atmosphere is a swirling mix of toxic gases. On the surface, it seems utterly inhospitable, a true celestial inferno. But here's the twist. Some scientists believe that this very planet, so hostile and alien, could one day become humanity's next great frontier. What if Venus, against all odds, holds the key to our survival beyond Earth? In this video, we'll uncover the daring vision of terraforming Venus, diving into the immense challenges it presents and the groundbreaking innovations that might just overcome them. By the end, you'll understand why this fiery neighbor continues to captivate the imagination of visionaries and whether it could, one day, be transformed into a thriving new home for humanity. Let's begin. At first glance, the idea of choosing Venus as a potential second home for humanity seems counterintuitive. After all, we're talking about a planet where the surface temperature soars above 800 degrees Fahrenheit. The air is packed with carbon dioxide, and clouds of sulfuric acid swirl endlessly in the sky. It's a vivid picture of a world that's actively hostile to life as we know it. So, why do scientists keep coming back to Venus as a serious contender for colonization? The answer lies in its surprising similarities to Earth and a few unique advantages that set it apart from other destinations in our solar system. For starters, Venus is often referred to as Earth's twin. This comparison isn't just poetic, it's rooted in some striking physical parallels. Venus and Earth are almost identical in size, with Venus being only slightly smaller. This means that its gravity is a lot closer to what we experience here on Earth. Gravity might not seem like a big deal at first, but it's a critical factor for any long-term human settlement. On Mars, for example, gravity is only about 1/3 of Earth's. Over time, reduced gravity can have major effects on human bodies, like weakening bones and muscles. Venus, on the other hand, offers gravity that is roughly 90% of Earth's, far closer to what our bodies are adapted to. Then there's Venus's location. Being the second planet from the Sun, it's much closer to Earth than Mars is on average. This proximity could make travel and communication between the two planets significantly faster and more practical. For example, a trip to Venus might take around 3 to 4 months using current spacecraft technology, while a journey to Mars can take 6 to 9 months or even longer, depending on the alignment of the planets. This reduced travel time could simplify the logistics of transporting people, supplies, and equipment for any colonization effort. But Venus's most intriguing advantage lies in its atmosphere. While the dense carbon dioxide-rich air at the surface makes the planet unlivable right now, that very density provides something we can't overlook: unparalleled protection from radiation. Unlike Mars, which has a thin atmosphere and no global magnetic field, Venus has a thick, insulating blanket of atmosphere that blocks out much of the Sun's harmful radiation. This radiation shielding would be crucial for human settlers, as excessive radiation exposure in space can lead to serious health risks, including cancer. Interestingly, the truly uninhabitable part of Venus is located at its surface. But higher up in the clouds, things take a fascinating turn. About 30 to 40 miles above Venus's surface, the pressure and temperature are much more Earth-like. In this sweet spot of Venus's atmosphere, the temperatures are manageable, and the pressure is similar to standing on the ground here on Earth. Many have theorized that this layer of clouds could host floating habitats, where humans might one day live in aerostats, essentially massive, balloon-like structures that remain suspended in the air. These habitats could take advantage of Venus's natural shielding from radiation while floating far above the planet's scorching surface. Of course, the challenges are immense, and we'll get into those as we explore the idea of terraforming Venus. But it's important to note that these advantages, Earth like gravity, robust radiation protection, and a relatively accessible location, have made scientists and engineers rethink what's possible. Venus is not just a hellish wasteland, it's a planet with untapped potential, waiting for innovation to uncover what might be possible. So, while Mars often steals the spotlight, perhaps it's time to take a closer look at our fiery neighbor and imagine what could happen if humanity chose to rise, literally, above its challenges. Transforming Venus into a livable world might sound like something out of science fiction, and for good reason. The planet presents some of the harshest conditions imaginable, each one a colossal challenge that would need to be addressed before humanity could even consider setting up a permanent home there. To begin with, the surface of Venus is staggeringly hot. Temperatures reach an average of 900 degrees Fahrenheit, hot enough to melt lead. This inferno is driven by a runaway greenhouse effect caused by Venus's thick atmosphere, which is almost entirely made up of carbon dioxide. On top of that, the planet's surface is shrouded by thick clouds of sulfuric acid, which reflect sunlight and trap heat, creating an environment where no human or machine could survive for long without extraordinary protection. But heat isn't the only extreme on Venus. The atmospheric pressure at the planet's surface is another life-threatening obstacle. Imagine standing at the bottom of Earth's deepest ocean trench. That's roughly what it would feel like to stand on the surface of Venus, where the pressure is 92 times greater than what we experience at sea level on Earth. For perspective, even some of the most advanced submarines couldn't withstand that kind of pressure. Any equipment, habitats, or vehicles would need to be designed to endure crushing forces that make our deepest ocean depth seem mild in comparison. And then there's the atmosphere itself. Venus's air is not only dense but also incredibly toxic. It consists primarily of carbon dioxide, with traces of nitrogen and clouds made of sulfuric acid droplets. Breathing, of course, would be impossible, and the acid in the atmosphere would corrode most materials we currently use for construction or machinery. The combination of toxicity, high temperatures, and intense pressure makes Venus's surface one of the most hostile environments in the solar system. It's no wonder some scientists joke that the only machines we could reliably send to Venus's surface are one-way missions. Even beyond these immediate physical challenges, Venus poses other unique barriers. The planet rotates extremely slowly, so slowly, in fact, that one day on Venus lasts longer than its entire year. This means that if we were to colonize the surface, we'd have to deal with one side of the planet baking under the sun's intense heat for months, while the other side plunged into freezing darkness. This slow rotation also impacts the planet's atmospheric circulation, creating winds at high altitudes that whip around the planet far faster than it rotates. On a practical level, this uneven distribution of sunlight and extreme weather patterns would make establishing a stable, predictable environment incredibly difficult. So when we talk about terraforming Venus, we're not just talking about flipping a few switches or building some shelters. We're talking about fundamentally re-engineering an entire planet. To cool the surface, for example, we'd need to address Venus's runaway greenhouse effect by either removing large amounts of carbon dioxide from the atmosphere or finding a way to reflect sunlight before it reaches the planet. Both ideas sound futuristic and ambitious, but they come with a host of technical challenges. Just to remove the carbon dioxide alone would require technologies that don't currently exist at the necessary scale. Cooling Venus could also involve constructing massive orbital mirrors to deflect sunlight, a feat that would demand engineering on a scale humanity has never attempted. Beyond cooling the planet, we'd also need to tackle the issue of atmospheric pressure. Some proposals suggest introducing chemical reactions that could solidify carbon dioxide into a form that sinks to the surface or is otherwise removed from the atmosphere. Others suggest the possibility of mining materials from Venus's own atmosphere to create floating habitats at higher altitudes where conditions are less extreme. But these solutions are still just theories, and many of them require technologies and levels of energy that are far beyond what we currently have. The hostile realities of Venus make it clear, terraforming this planet isn't just about solving one problem. It's about tackling a cascade of interdependent challenges, each one demanding a level of ingenuity and innovation that pushes the boundaries of what humanity is capable of. But perhaps that's the allure of Venus. Its challenges demand bold thinking and the kind of advancements that could unlock technologies we can't even imagine today. After all, the very idea of reshaping an entire planet might feel impossible right now, but so did flying, exploring space, and so many other milestones we've achieved through human ingenuity. So, as daunting as Venus's realities may be, they serve as a powerful reminder of how far we've come and how far we might yet go. Terraforming may sound like the plot of a science fiction blockbuster, but at its core, it represents the intersection of cutting-edge science, engineering, and extraordinary ambition. The idea is straightforward in principle: to transform an uninhabitable planet into one that supports life. But as you might expect, the reality is anything but simple. When it comes to Venus, terraforming would involve addressing its most hostile features, cooling the planet, reducing its overwhelmingly carbon dioxide-dominated atmosphere, and potentially jump-starting a stable water cycle. Let's break this down step by step to better understand what this monumental process might entail. First, cooling Venus is one of the biggest challenges, and it's not as simple as flipping a cosmic thermostat. As we covered earlier, Venus's thick atmosphere has trapped heat in a runaway greenhouse effect, making its surface temperatures hot enough to rival the inside of a pizza oven. To combat this, we'd need to reduce the amount of solar energy that reaches the planet in the first place. One theoretical proposal involves deploying giant mirrors or sunshades in orbit around Venus. Picture colossal reflective panels hundreds, maybe thousands of miles wide that could block or redirect sunlight away from the planet. These massive structures would gradually lower surface temperatures, potentially over decades or centuries. Another cooling strategy ties directly into altering the atmospheric composition. Venus's atmosphere is almost entirely carbon dioxide, with trace amounts of nitrogen and extremely small amounts of water vapor. To reverse the greenhouse effect, we'd need to remove or transform vast quantities of carbon dioxide. This is where atmospheric engineering comes into play. One idea involves triggering chemical reactions to convert carbon dioxide into solid or liquid forms that could be stored or sequestered on the planet's surface. For instance, we could theoretically introduce elements like calcium or magnesium, which react with carbon dioxide to form solid carbonates. But here's the catch: the sheer scale of Venus's atmosphere means this would take an astronomical amount of resources and energy, far beyond anything humanity currently possesses. Alternatively, some have suggested using advanced microbes or bioengineered organisms to consume carbon dioxide and convert it into less harmful byproducts. Imagine bioengineered bacteria that could thrive in Venusian conditions, working overtime to alter the atmosphere gradually. Again, while these ideas are fascinating, they remain firmly in the realm of theoretical science for now. Cooling and transforming the atmosphere are just the beginning. To make Venus truly habitable, liquid water would likely need to exist on its surface. Currently, Venus is bone dry, with an atmosphere so hot that any water molecules are broken apart before they can form liquid droplets. This means we'd need to introduce a hydrological cycle, essentially bringing water to the planet and ensuring it can remain stable. Some extreme proposals suggest bombarding Venus with icy comets or asteroids rich in water. The energy from these impacts would simultaneously cool the planet and deliver the necessary water to potentially form oceans, lakes, and rivers. Other ideas involve extracting hydrogen from Venus's upper atmosphere and combining it with oxygen to create water through chemical processes. However, both approaches would take monumental effort and technological advancements far beyond anything currently achievable. Then there's the challenge of creating an Earth-like climate. Even if we manage to lower temperatures, reduce carbon dioxide, and introduce water, we'd still need to maintain this carefully balanced system over the long term. That means regulating atmospheric pressure, ensuring stable weather patterns, and possibly introducing vegetation to jump-start an ecosystem. Forests, for instance, could play a role in absorbing carbon dioxide and releasing oxygen, gradually shifting the atmospheric composition to something more breathable. But growing plants requires fertile soil, nutrients, and light, all things Venus currently lacks. These efforts would take centuries, if not millennia, and require us to become masters of planetary engineering. Essentially, we're talking about manipulating an entire planet's systems, its atmosphere, temperature, water cycle, and ecosystems, all while working around the unique hazards Venus presents. The sheer scale of such an undertaking raises legitimate questions. Do we have the technological capacity to make this happen? And even if we did, should we? While the science behind terraforming is still in its infancy, it's amazing to think about how far human ingenuity could take us. For now, these ideas remain largely theoretical, but they build on principles we're already exploring here on Earth, like carbon capture, climate engineering, and sustainable ecosystems. If we ever reach the point where terraforming is feasible, it would mark one of humanity's most transformative achievements, the ability to re-engineer worlds and expand the boundaries of what's possible. And Venus, despite its current hellish state, might just be the ultimate proving ground for such bold and groundbreaking ideas. Before we even think about transforming the surface of Venus into a livable environment, scientists have proposed a more immediate and achievable starting point: floating habitats in Venus's upper atmosphere. At around 30 to 40 miles above the planet's surface, conditions are surprisingly Earth-like compared to the inferno below. Here, the temperature ranges from 70 to 80 degrees Fahrenheit, comfortably within the range that humans can tolerate, and the pressure is roughly equivalent to what we experience on Earth at sea level. This relatively hospitable layer has captured the imagination of researchers as a potential stepping stone for colonizing Venus. Massive, floating cities called aerostats. Aerostats are essentially large, lighter-than-air structures designed to float in Venus's dense atmosphere. Because the planet's atmosphere is rich in carbon dioxide, which is over 50% denser than air, structures filled with breathable air made of oxygen and nitrogen would naturally float, much like helium balloons rise in Earth's atmosphere. This means that building and sustaining these habitats wouldn't require exotic or impossible technology. The basic principle is already well understood and used in lighter-than-air crafts here on Earth, like blimps. These floating habitats could take on a variety of designs. Imagine enormous, balloon-like modules tethered together, each one equipped with advanced life support systems, solar panels for energy, and protective materials to shield against the trace amounts of sulfuric acid present even at these higher altitudes. These aerostats wouldn't just be isolated bubbles of human activity. They could form interconnected cities, complete with living quarters, agricultural facilities, research labs, and everything needed to sustain a human population for an extended period. But why start in the atmosphere instead of the surface? The answer comes down to practicality. By living in the upper atmosphere, we bypass nearly all of Venus's most hostile conditions. We avoid the extreme heat, nearly crushing atmospheric pressure, and corrosive environment found at ground level. In these floating habitats, humans could work safely, conduct research, and begin laying the foundation for larger-scale projects like terraforming. Building floating cities in Venus's atmosphere wouldn't just be a technological showcase, it would also serve as a critical testing ground. Researchers could study Venus's atmosphere up close, refine their understanding of its climate and chemistry, and experiment with methods to alter atmospheric composition. For example, they might explore ways to extract carbon dioxide or develop techniques for capturing and utilizing sulfur compounds. The knowledge gained from these efforts would be invaluable for any future attempts to terraform the planet. These habitats could also be hubs for resource harvesting. Venus's atmosphere is rich in elements like carbon and sulfur, which could be extracted and converted into materials for construction, energy production, or even fuel. Advanced robotic systems and AI-driven manufacturing could play a key role in setting up facilities that sustain these cities and support human residents. Critically, floating cities offer another huge advantage: their relative proximity to Earth. Venus is closer to us than Mars, and its atmospheric layers provide natural protection against solar radiation, eliminating one of the biggest risks of long-term space habitation. Communication with Earth would also be faster due to its shorter distance, making it easier to coordinate missions, resupply efforts, and emergencies. The concept of aerostats may sound futuristic, but it's not as far-fetched as one might imagine. Early designs suggest that constructing prototypes to test this technology could happen within the next few decades. These early habitats could be small, automated research stations, paving the way for larger, human-occupied cities once the technology is proven. And while starting with floating cities may seem like a baby step compared to the vision of fully terraformed planets, it's a practical and achievable first step toward making Venus a part of humanity's future. So, floating habitats wouldn't just be a way of dipping our toes into colonizing Venus, they'd be a transformative leap forward. By creating sustainable homes in the skies of another world, we'd not only redefine what it means to live beyond Earth, but also gather the insights and experience needed for even grander projects. In many ways, these floating cities could be humanity's first true foothold in transforming Venus from a fiery wasteland into a place we could one day call home. One of the most daunting challenges of terraforming Venus is, without question, its extreme temperatures. With surface heat averaging around 900 degrees Fahrenheit, it's a world locked in a cycle of unrelenting radiation and suffocating heat, driven by its runaway greenhouse effect. Cooling Venus isn't just a minor adjustment. This is about overcoming one of the most extreme planetary environments in the solar system. So, how could we take a planet that's currently as hot as an industrial furnace and make it cool enough for humans to inhabit? Several ambitious proposals have been put forward, each one as daring as it is groundbreaking. One of the most talked about ideas involves deploying an orbital solar shade. Imagine a colossal structure positioned in space between Venus and the Sun, designed to block sunlight before it even reaches the planet. By reducing the amount of solar energy hitting Venus, the surface would start to cool gradually, potentially reversing the extreme greenhouse effect over time. To put the scale of this project into perspective, such a shade would need to be enormous, perhaps the size of Venus itself, in order to cast a shadow large enough to significantly impact the planet's temperature. Engineers have suggested building the shade out of ultra-lightweight materials like graphene or reflective membranes to make it feasible to construct and deploy in space. But how would we keep such a structure in place? Some concepts involve positioning the shade at a specific orbital point known as the Lagrange point, where the gravitational forces between the Sun and Venus would keep it relatively stable. Others suggest actively propelling the shade using solar sails or ion propulsion systems to ensure precise alignment. While the idea of a massive solar shade might seem like science fiction, the basic principles of shading and solar energy deflection are grounded in established physics. The real challenge lies in the engineering, building something this vast, assembling it in space, and maintaining it over the decades or even centuries it would take to achieve meaningful cooling. A related concept involves using giant orbital mirrors instead of shades, not to block sunlight entirely, but to reflect excess solar energy away from the planet. These mirrors would work like an enormous reflective blanket, redirecting light and heat back into space. One advantage of mirrors is that they could potentially be smaller than a full solar shade and deployed in modular segments, making the project slightly more manageable. Additionally, mirrors could be adjusted or reoriented over time to fine-tune their effects, giving scientists more control over the cooling process. The reflective mirrors could even serve a dual purpose, helping lower Venus's temperatures while simultaneously generating electricity by concentrating sunlight onto solar panels for energy production. Another bold idea builds on the concept of geoengineering Venus's atmosphere to aid in cooling. For example, introducing reflective particles or aerosols into the upper atmosphere could mimic the natural cooling effect seen on Earth after volcanic eruptions. When large volcanoes erupt, they release sulfur dioxide and other particles into the stratosphere, which reflect sunlight and temporarily lower global temperatures. On Venus, this strategy could be scaled up, using advanced technology to pump reflective materials into the atmosphere and create a planet-wide cooling effect. The challenge here is how to maintain this system long-term without eventually overwhelming the atmosphere with additional particles or creating unintended side effects. Some scientists have also explored the idea of physically removing parts of Venus's atmosphere to reduce the temperature. This could involve massive orbital platforms or robotic systems that actively extract carbon dioxide from the atmosphere, converting it into solid or liquid forms that could be stored or even launched into space. While this approach tackles both the heat and the overwhelming pressure at Venus's surface, the sheer amount of carbon dioxide, about 90 times more than Earth's atmosphere, would make this a Herculean task. For all their ambition, these proposals highlight the immense scale of what it would take to cool Venus. The size and scope of these projects would far exceed anything humanity has ever attempted, requiring breakthroughs in materials science, energy production, and large-scale engineering. However, they also inspire a powerful sense of possibility. The fact that we're even discussing plans to reshape the climate of an entire planet speaks to humanity's ability to dream big and think beyond the limits of what seems achievable. Could an orbital solar shade or reflective mirrors one day cool Venus enough to make it habitable? The truth is, no one knows for sure. But these ideas represent the first steps in exploring solutions to one of the most significant challenges we'd face in terraforming any planet. They also hint at how the technologies we're developing to combat climate change here on Earth, like carbon capture and solar geoengineering, could one day be scaled up for planetary use. Cooling Venus may seem like an impossible dream, but every great achievement in human history started with ideas that once seemed just as far out of reach. Perhaps one day, future generations will look back on this moment as the beginning of humanity's boldest and most transformative adventure. While cooling Venus is one monumental challenge, tackling the planet's toxic atmosphere is an entirely different beast. Venus's atmosphere is dominated by carbon dioxide, which makes up over 96% of its air composition. Not only does this drive the runaway greenhouse effect that heats the planet, but it also makes the air completely unbreathable for humans or any form of Earth-based life. To transform Venus into a habitable world, we'd need to re-engineer its atmosphere on a planetary scale. The question is, how do we turn a dense, deadly mix of carbon dioxide and sulfur dioxide into something humans can breathe? Scientists have proposed a few intriguing and highly ambitious solutions, ranging from engineered biology to massive chemical engineering projects. One of the most fascinating ideas involves using genetically engineered microbes designed specifically for Venus's hostile environment. On Earth, we already have microorganisms like cyanobacteria that are capable of photosynthesis, converting carbon dioxide and sunlight into oxygen. Theoretically, we could bioengineer similar microbes to thrive in Venus's upper atmosphere where conditions are less extreme. This region, about 30 to 40 miles above the surface, has temperatures and pressures comparable to those on Earth. If we could seed the atmosphere with these microbes in large enough quantities, they might gradually start to convert carbon dioxide into oxygen, essentially kickstarting a biological transformation of the planet's air. The concept of using microbes to terraform a planet isn't as far-fetched as it sounds. On Earth, cyanobacteria are thought to have played a major role in the Great Oxygenation Event billions of years ago, when they filled our atmosphere with oxygen, paving the way for complex life to evolve. Could microbes engineered for Venus do the same? The challenges would be immense. Venus's atmosphere doesn't just contain carbon dioxide, it also has sulfuric acid clouds and virtually no water. To survive, any microbes introduced to the planet would need to be resistant to acid, able to extract hydrogen from trace amounts of water vapor or other sources, and endure high levels of ultraviolet radiation from the sun. Engineering organisms with these traits would require advancements in genetics and synthetic biology far beyond what we currently have, but the idea is an exciting glimpse into what might one day be possible. If biological approaches aren't viable, or if we need faster results, chemical engineering offers another path. One proposal involves deploying massive robotic systems or atmospheric processors designed to chemically alter carbon dioxide. These machines could operate much like carbon capture technology on Earth, but on a far greater scale. For example, they could extract carbon dioxide from the atmosphere and convert it into solid carbon or carbon-based compounds like graphite, which could then be deposited on the planet's surface. Alternatively, the carbon dioxide could be broken down into its components carbon and oxygen through chemical or electrochemical reactions. Released oxygen could potentially contribute to a breathable atmosphere, while the carbon could be stored or repurposed. One particularly ambitious idea involves introducing vast quantities of reactive metals, such as calcium or magnesium, into Venus's atmosphere. These metals could react with carbon dioxide to form stable carbonates, effectively locking away the gas in solid form. While this approach could theoretically remove large amounts of carbon dioxide, the sheer logistics of transporting and deploying enough material to impact the atmosphere of an entire planet would be staggering. Still, it highlights the type of large-scale thinking required to tackle a challenge of this magnitude. Another intriguing proposal combines atmospheric transformation with resource extraction. Venus's atmosphere is rich in carbon, nitrogen, and sulfur elements that are vital for manufacturing and construction. By deploying advanced robotic systems or factories in the upper atmosphere, we could potentially harvest these elements for use in building habitats, generating energy, or even creating fuel. Dual-purpose systems that both sequester carbon and produce useful resources could make the process more efficient and sustainable over the long term. But even if we succeeded in removing or converting most of Venus's carbon dioxide, we'd face yet another hurdle, ensuring that the atmosphere remains stable. On Earth, a complex interplay of ecosystems, weather patterns, and geological processes keeps our atmosphere in balance. On Venus, we'd need to artificially create and maintain such equilibrium, potentially using advanced climate control technologies to regulate temperature, pressure, and gas composition. This would require constant monitoring and adjustments, turning atmospheric engineering into an ongoing process rather than a one-time fix. So, could we transform Venus's toxic air into something breathable? Theoretically, yes, but it would demand technologies and innovations far beyond what humanity currently possesses. These strategies, whether biological or chemical, represent the bleeding edge of science and engineering, pushing the boundaries of what's possible. And while the challenges are massive, the potential rewards are equally extraordinary. If we could successfully transform Venus's atmosphere, it wouldn't just give us another planetary home. It would redefine our understanding of what's achievable and mark a new chapter in humanity's story as a truly interplanetary species. Terraforming a planet like Venus isn't just one of the most ambitious scientific or engineering challenges humanity has ever imagined, it's also an ethical minefield. While the allure of creating a new, habitable world for humanity is undeniable, it forces us to grapple with some difficult questions about our role in the universe, our responsibilities to other planets, and even our priorities as a species. Do we, as humans, have the right to drastically alter an alien world? And if so, at what cost? Exploring these questions is just as important as tackling the technical obstacles, because the decisions we make now will shape the way future generations view our place in the cosmos. To start, let's examine the core issue. Do we have the moral authority to transform a planet like Venus? On the surface, it seems harmless. Venus, as far as we know, has no life, no ecosystems, and no intrinsic features that would appear to be disrupted by terraforming efforts. But does the absence of life give us a blank check to modify an entire planet? Some argue that planets, as natural entities, have inherent value even without life. By altering Venus, we'd essentially be imposing humanity's will on something that has existed for billions of years without us. There's a philosophical weight to that decision, one that forces us to reflect on whether our technological capabilities should always be exercised simply because they exist. In our drive to expand and survive, are we playing the role of creators or conquerors? Then there's the cosmic ripple effect to consider. In creating a new Earth on Venus, are we irreversibly altering its future scientific significance? Venus provides a valuable window into planetary science. Its extreme conditions are a living laboratory for understanding phenomena like the greenhouse effect, atmospheric dynamics, and the evolution of planets. If the planet is terraformed and fundamentally altered, we could lose the chance to study it in its natural state, potentially missing insights that could help us better understand not just Venus, but also Earth and other worlds. Scientists call this the preservation argument, and it raises the concern that by terraforming, we might be erasing something precious that future generations could deeply value. But the issue isn't just about Venus itself, it's about the lessons we bring from our home planet. Humanity's track record with our own environment hasn't exactly been perfect. From deforestation to climate change, we've struggled to balance development with ecological sustainability. So, before we set our sights on fundamentally changing another planet, shouldn't we first prove that we can take better care of the one we already have? Critics of terraforming argue that it's an expensive distraction from more pressing issues here on Earth. Billions, if not trillions, of dollars would be required to terraform Venus, money that could instead be spent on combating climate change, reducing poverty, or developing renewable energy solutions. After all, if we can't manage Earth's climate, what makes us think we can succeed on a planet as hostile as Venus? On the other hand, proponents of terraforming argue that it's not about abandoning Earth, it's about securing humanity's survival. Earth faces countless existential risks, from natural disasters to potential asteroid impacts, and creating a backup home for humanity might be the best way to ensure our species endures. Terraforming Venus could also accelerate the development of groundbreaking technologies, including advanced methods of carbon capture, atmospheric engineering, and renewable energy innovations that could benefit Earth as much as they benefit our interplanetary ambitions. Supporters see terraforming as a long-term investment, one that complements rather than competes with efforts to save our own planet. Finally, there's the question of unintended consequences. Even with the best intentions, how do we guarantee that our efforts to terraform Venus won't lead to unforeseen ecological or planetary disasters? What if we create a runaway system that destabilizes the planet entirely, making it even more uninhabitable than before? What if our technologies, once unleashed, have effects beyond Venus, potentially altering the delicate balance of forces in the solar system? These are the kinds of questions that remind us terraforming isn't just a technical exercise. It's a moral and philosophical challenge that requires us to weigh long-term risks and benefits carefully. In the end, debating the ethics of terraforming isn't about finding easy answers, it's about asking the right questions. Do we have the right to become the architects of a new world? Should we prioritize fixing what's broken here at home before reaching for the stars? And if we do choose to alter an alien planet, how can we ensure that we do it responsibly, for the benefit of everyone, not just for the sake of progress? These are questions humanity must confront together, not just as explorers, but as stewards of the universe. While terraforming Venus feels like an impossibly distant dream right now, the pace of technological advancement has a way of transforming science fiction into reality. Many of the innovations required to make Venus habitable don't yet exist, but by looking at the trajectory of emerging technologies, we can start to imagine how humanity might one day tackle the monumental challenges of re-engineering an entire planet. From harnessing unprecedented energy sources to constructing structures in the vacuum of space, the tools of tomorrow could make terraforming Venus a possibility in the centuries to come. Let's start with energy. Transforming a planet like Venus would demand an almost unimaginable amount of power, far outstripping what humanity can generate today. However, one promising solution lies in nuclear fusion, the process that powers the sun. Unlike conventional nuclear fission, which splits heavy atoms, fusion works by combining light atoms like hydrogen into helium, releasing massive amounts of energy in the process. The result, a near-limitless clean energy source that could power everything from atmospheric processes to massive orbital mirrors or sunshades. While nuclear fusion remains elusive today, with experimental reactors like ITER still in development, scientists are optimistic that breakthroughs in the coming decades could finally unlock its potential. If fusion becomes a reality, it could provide the sustained energy output needed for large-scale projects like cooling Venus or converting its dense carbon dioxide atmosphere into something more hospitable. Another key innovation could come from advances in materials science. To terraform Venus, we'd need structures capable of withstanding its unique challenges like intense heat, high pressures, and corrosive sulfuric acid clouds. Enter graphene, an ultra-lightweight yet incredibly strong material composed of a single layer of carbon atoms. Graphene is not only heat-resistant but also highly conductive, making it an ideal candidate for building everything from solar-powered energy collectors to atmospheric processing stations. Its strength-to-weight ratio also makes it a game-changer for creating large-scale orbital structures, such as the sunshades or reflective mirrors we discussed earlier. If materials like graphene can be mass-produced affordably, they could revolutionize construction both on and above Venus. Space-based construction techniques could also play a pivotal role. In recent years, automation and robotics have advanced rapidly, and these technologies are laying the groundwork for entirely new methods of building in space. Imagine fleets of autonomous robots deployed not only to assemble massive orbital mirrors and sunshades, but also to harvest resources directly from Venus's upper atmosphere. These robots could work continuously in extreme conditions without the need for human intervention, drastically reducing costs and risks. Meanwhile, breakthroughs in 3D printing are already reshaping how we think about manufacturing. In the future, 3D printing could enable the construction of floating habitats, atmospheric processing units, or even solar reflectors using materials harvested directly from Venus or other celestial bodies. Speaking of floating habitats, another technology that could be crucial is advanced aerostat systems. Floating cities high in Venus's atmosphere could serve as humanity's first foothold on the planet, acting as research stations and testing grounds for terraforming technologies. Developing self-sufficient habitats complete with closed-loop life support systems, modular construction, and efficient recycling technologies would be a critical step toward long-term colonization. We're already seeing early versions of these systems being tested on Earth in extreme environments and aboard the International Space Station. Scaling them up for Venus's unique conditions will require significant innovation, but the groundwork is being laid today. Then there's artificial intelligence. AI could become the brain behind any terraforming effort, analyzing data, designing efficient systems, and managing complex processes that would be impossible for humans to oversee manually. For example, AI algorithms could monitor atmospheric conditions in real time, adjusting carbon scrubbing technologies, optimizing solar reflectors, or even coordinating the efforts of thousands of robotic systems working across Venus's surface and atmosphere. By taking on tasks too complex or dangerous for human operators, advanced AI could dramatically accelerate the terraforming process. Finally, we can't overlook advancements in interplanetary transportation. For humanity to deploy the equipment and resources needed to terraform Venus, we'll need reliable, cost-effective space travel. Innovations like reusable rockets being pioneered by companies like SpaceX are already slashing the cost of getting to space. Looking further ahead, concepts like nuclear propulsion or even space elevators could drastically improve our ability to transport people and materials between Earth and Venus, or even utilize resources from other parts of the solar system, like the asteroid belt, to fuel terraforming efforts. While many of these technologies are still in their infancy, they represent a future where humanity might have the tools needed to reshape an entire planet. The road to terraforming Venus will be long, and success is far from guaranteed. But the rapid pace of innovation suggests that what seems impossible today could become achievable tomorrow. After all, the human story has always been one of pushing boundaries, whether it's mastering fire, harnessing electricity, or venturing into space. Transforming Venus may be the ultimate expression of that drive, requiring not just advanced technologies, but also the vision, determination, and cooperation of future generations. Humanity's future has always been driven by a spirit of exploration, the desire to venture beyond the horizon, to test the limits of what's possible, and to create a better world for future generations. As we gaze up at the night sky, it's impossible not to wonder, could the stars hold the key to our survival? Venus, with all its extremes and untapped potential, presents one of the most fascinating possibilities for a second home. But as we've explored, the path to making Venus habitable would be unlike anything humanity has ever attempted. It would demand not just technological innovation, but also bold vision, relentless determination, and most importantly, unprecedented global collaboration. The prospect of transforming Venus is a reminder of how far we've come as a species. From the first controlled fire to the construction of towering megacities, from simple wooden boats to spacecraft capable of reaching other planets, humanity has consistently proven its ability to tackle grand challenges. And yet, terraforming Venus would be on an entirely different scale, turning a lifeless, hostile world into a thriving extension of human civilization. It wouldn't just be an engineering feat, it would be a declaration that we're not bound by the limits of Earth, but with such potential comes responsibility. The decisions to pursue such an ambitious goal would force us to confront profound questions about ethics, sustainability, and our relationship with the universe. One of the most inspiring aspects of a project like Terraforming Venus is its potential to unite humanity. The effort would require the pooling of resources, expertise, and creativity from every corner of the globe. Scientists, engineers, policymakers, and everyday people would need to work together, setting aside differences to focus on a shared vision of the future. In many ways, the challenge of Venus could mirror and amplify the collaborative efforts we've seen in tackling global issues like climate change and space exploration. Just as the Apollo missions inspired the world to dream bigger, the endeavor to reshape a planet could galvanize humanity to work toward a common goal, proving that even the most insurmountable challenges can be overcome when we align our ambitions. Yet, it's also worth reflecting on what such a monumental project would mean for us here on Earth. Before we reach for the stars, are we ready to take responsibility for the planet we already call home? The lessons we've learned and continue to learn about managing Earth's ecosystems and addressing climate change would be essential in shaping a sustainable future on Venus. But more than that, these lessons remind us that our stewardship of Earth is critical, not just as a moral obligation, but as a foundation for our success in any interplanetary endeavor. The technologies and innovations developed for terraforming could even help us heal our planet, proving that the push to explore the universe need not come at the expense of the world we already have. As we look ahead, the idea of making Venus habitable isn't just about survival, it's about evolution. It's about imagining what humanity could become when we finally step beyond our cradle and into the wider cosmos. Could we transform not only a planet but ourselves into a species capable of thriving among the stars? Could we take the lessons learned from Venus and apply them to forge a sustainable, unified future both on Earth and beyond? Perhaps the real significance of these questions isn't just in finding answers, but in daring to ask them at all. The challenges are immense, the questions are complex, and the timeline stretches farther than we can easily imagine. But it's the dream of what could be that pushes us forward, a vision of humanity embracing its role as both the caretaker of its home and the shaper of its destiny. Whether Venus becomes our second home or simply a stepping stone to a larger interstellar journey, one thing is certain: the pursuit of this dream will redefine what it means to be human. If you've enjoyed diving into the possibilities of terraforming Venus, we'd love to hear your thoughts. What excites you most about the idea? What challenges do you think we'll face? Be sure to like, subscribe, and share your perspective in the comments below. The future of humanity may be written among the stars, and together we can dream of where we'll go next.